Hi everyone, and welcome to the second session of the EO for Agriculture Under Pressure workshop. My name is Belen Franch. I work as Distinguished Researcher at the University of Valencia and as Adjunct Professor at University of Maryland. I co-chaired this session with Jose Moreno from University of Valencia. The session is grouped as climate change adaptation, monitoring stressors, supporting increased resilience and risk management, changing growing conditions, extreme events, and agro-insurance, including flood monitoring, damage characterization, and among others. We will have 5 presentations. Each will last 15 minutes, followed by 5 minutes questions and answers. We will conclude the session with 20 minutes of discussion and answer for further questions that may arise. Before starting the session with the first speaker, I wanted to introduce Jose Moreno so he can introduce himself.
Hello, good afternoon. Welcome to the session. My name is Jose Moreno. I am Professor of Earth Physics at the University of Valencia and also in charge of the Laboratory for Earth Observation in Valencia, where we are developing a number of applications in agriculture by using mostly Sentinel-2, but also synergy between Sentinel-1 and Sentinel-2. And before introducing the first speaker, I would like to remember you that today we will have these 5 presentations, then the 20 minutes discussion. But another objective of this workshop is also to collect ideas and recommendations for future activities in this field. So please join us also for the requirements booth, which will take place 1 hour after the ending of the session, where you can put both the questions to the speakers or questions to the audience in general, because everybody will be allowed to give answers. And also you can put ideas or recommendations for future activities in this area of Earth observation for agriculture. So please stay with us for this requirements booth at the end of the session. And after this introduction, I will give the floor to the first speaker today, which is Oscar Rojas. He will give a presentation about the strengthening national agricultural drought monitoring system based on EO data. Oscar, the floor is yours.
Yes, I would like to share with you the experience that we in FAO we are doing to strengthen national agricultural drought monitoring system using Earth observation. This presentation was participated by Mario Zappacosta, that is the Senior Economist of Trade of Market Division, and myself, my name is Oscar Rojas, from the Office of Climate Change, Biodiversity, and Environment. The main thing is, what is ASIS, that is the agricultural stress system? We developed this some years ago to support the global information and early warning system to detect hotspots around the globe that can affect food security. And this is supporting this at global level. This is working 1 kilometer resolution using the top data that was extended from NOAA starting in 1985. And this is an expert system that will mimic what normally a remote sensing expert will do when they analyze remote sensing information in agriculture. But from this kind of development, we decide to go to what we call country-level ASIS or next-generation ASIS. The idea is to support now countries with the same information, but in this case, we go more in detail. We need to calibrate at country level, and we will be adapt to the country needs. This kind of system is, the idea is to be automatic and will be mimic all based in the in big data and learning machine system. Then it will be support and will be established in the institutions, in the national institutions. What the next generation ASIS offer to the countries? They can be calibrated conditions. That means that current land cover studies using high resolution will be used and will introduce as a crop specific. What we need is the countries to know where are the beans, where are maize, where are the sorghum, and then we can analyze all this information crop specific. Another important thing that the system provides is that we introduce the crop coefficients. What does mean? The water requirement that is specific for sorghum, for maize, and this will give the sensitivity to any phenological phase. That means that water stress happens during flowering and grain filling going to have more weight in the temporal integration. From the global, we have a model to define a start of season and the season. But in the case of countries, we are requesting to the countries at administrative level, district, municipality, to provide when most of the farmers plant and what is the most variety, the length of the variety that they use. Then we are going to use this information from the ground. And we have the possibility to monitoring the different number of crop seasons. Sometimes we have one, but in other country you have two. In Central America, you have 3 crop seasons in a year. Then this is possible to do. The advantage of the system that we propose is that is temporal and spatial integration. These 2 characteristics give the possibilities that maybe most of the systems in your observation don't have, that will give for each crop season, for each crop, a summary, annual summary. And how they do this is because you have the possibility to, every time that you receive, every 10 days, an image, you are going to integrate. For instance, if you have here 2 pixels, one that is the arrow red and the other in green, both pixels have different time of planting, but they're going to integrate during the start of season up to the end of season. They will be temporally integrated and going to be multiplied by the crop coefficient. As soon as you are doing this integration temporal, you are going to pass to the spatial integration. What is going to mean is that we are going to use the land cover map and the area where are the crops in the country level will be, where are the maize, where are sorghum. We are going to count only in the crop areas that here is in yellow, and we are going to count how many pixels was classified as a drought pixel. In this case, will be expressed as a percentage, that will be the percentage of crop area affected by drought. In this example, is 70% will be affected. This is ASI in this specific case. In this example, for instance, we receive the Vegetation Health Index on the top, 1 kilometer resolution in Mexico, but they will be multiplied and integrated temporally by the crop coefficient. And you see here the small dots that is in the map of the middle. There is the crop mask, and these crop masks will going to do the spatial integration, and at district level, you are going to see, or the user going to see in red the areas that are severely affected, in yellow moderate affected, in green the areas that doesn't suffer from water stress. ABC don't want to. I think they're freezing my PowerPoint. Sorry, I think I have to close and connect because it stopped working.
Maybe you can start again.
Yes, I'm going to stop. I'm going to close, and I'm going to. Let me know you receive.
Yes, yes.
Okay, good. Excellent. Then what we have here is, in this case, we provide to the countries agricultural drought monitoring system and early warning. In this, the advantage of this is that the user don't have to see all the anomalies like in the classical way, because ASIS is temporal and spatial integrated. If you see only the maps that are in the bottom, you see the last one, you don't need to see what happened before because everything is considered and also multiplied by the current coefficient. Then you need to, you simplify this kind of process to the user. Sorry, it's things that start to block every time. I don't know why. I'm going to launch again. Okay, we have here the case of Guatemala. In this case, you see the areas from high resolution land cover, the maize areas. You have here the classification of each pixel during the crop season, the percentage of area affected at pixel level, but this is summarized for decision maker and user in the administrative unit that have been affected. Also, we provide other index like here, that is the drought category, that they can give the idea of the decision maker, where are the extreme drought affected the crop areas, where is the severe, moderate, mild, and so on. Sorry, I have to do it again. Let me to close the...
Maybe you are using the wrong key to advance the slide, so try another.
Yeah, can you try to switch between the slides when you are connected?
We'll try to do. Let me see, we are here. Let me see, do you receive my screen?
Yes.
Yeah.
Okay, let's see if there are no more problems. Sorry about that.
Can you try to switch now between two slides just to test? Okay, perfect.
Yes, things is working, but certain moment they proceed. Okay, what we offer also is a historical database. So we have the different hotspots, as I mentioned before, you have the summary, and then you can, in this case, in Honduras, you can compare during the 91, 92 El Niño phenomenon that was affecting many countries of the world in the agriculture areas because due to this El Niño. You can compare with 2001 or 2004, that is another El Niño. You can see the severity during the first crop season in the maize areas of Honduras. That is interesting because because you have more than 30 years, you can make the calculation of the historical drought probability at an administrative level, and then you have more than, in the first, you have more than 20% of the areas affected by administrative level, 30% or 50%. This gives the possibility to the governments, to guide the government, these maps, where they should do the public investment or how to prepare financial proposals. Because if you are implementing a irrigation system or harvest or rain harvest, it should be done in these areas that are more prone. Also, what is possible to do to the system and what we intend is to link with the action. It's important that now our system have to react, or to give the possibility to the governments to react. And then we are linking the system and the different categories with the national drought mitigation plans. That means if you have a moderate drought, you have some series of activities that the Ministry of Agriculture, Ministry of Health should do to mitigate and to avoid to pass to emergency. But in the case that you have crop failure identified by the system, you also in the national mitigation plan, you have to be coordinate how to respond to the emergency. We can also use the system to trigger financial mitigations activities to the agricultural drought. In this case, we have in Nicaragua two data from two different districts or municipalities. On the left, we have Esteli, that there are 2 extreme events in the last 30 years, and the trigger will be when ASI have the value of 40%. In the case of Nagarote, you have 3 extreme events, and then the trigger will be higher, in this case 60% to cover the extreme events. Of course, we are talking about a parametric crop assurance. All the farmers inside Nagarote will be paid off when reach 60%, but the premium will be higher in the case of Esteli that have less prone to drought. And this is very interesting. And also, if you want the financial mechanism be sustainable, you can introduce a deducible. That means that you can pay the 100% of indemnity when you have a catastrophic event. But for the moderate event, you can reduce due to the impact, and you introduce a deducible, and there are going to be a certain threshold that the crop assurance will not pay. Also, a very, very interesting application that have the ASI is the probability to forecast. And then you can see here in this example is Puno in Peru with oats. You can forecast 2 months and a half before the end, before the physiological maturity. The physiological maturity in Puno is in May, but you can forecast how will be the situation at the end of February. That's been that this in 89, 90, that was a big drought. You can see how in February you can also identify the areas that will be suffer of crop failure. In the case of moderate drought, in 2006 to 2007, is also well identified the areas that will be suffer from drought. And in a normal drought, in a normal crop season, there are no water stress, also is working the forecast. Then this is something that is very interesting to test in the different countries and could allow them to implement mitigation activities with 2 months and a half before the end of the crop season. Then the government can identify they have a food security problem, or they could be affect the commercial balance. Sorry, again happened.
Oscar, you have like 3 minutes left.
Yeah, sorry, it's the problem of. Okay, I have 3 slides, I think, only. We developed a customized website that they're going to pick up all the information and going to run automatically the information analyzed like I already showed to you, and all the indices will present in automatic way with any intervention, human intervention, to the specific website. The website in this case is Mexico and can be customized with different logos, photos, or whatever, and people can compare inside the website all the indices that I showed you. Also, we developed a platform. In the country has a health portal. This is very interesting because in this case, we are not using quick looks, we are using the raster data, and we identify the hotspot and can overlay with socioeconomic data, like in this case, rural population, but could be poverty indices of livelihood. This is something that gives more information to the decision maker when they have to take some decision. My final remarks are, to be really effectively support countries on drought, early warning, on any climate disaster, we need to offer to them optimized system based in error observation. These systems need to be transferred to the country with certain level of customization to guarantee the ownership. This is something very important that they can accept. National office instant to do all the calculations that we normally train in there. They will dedicate to confirm the accuracy of the system and give feedback to the a relation with the discrepancies to the expert, and this expert have the possibility to improve the algorithm of analysis, and this will be at the end improving the machine learning process on the identification of whatever risk, climate risks we were talking. And finally, the system must be linked to the action to resolve a specific problem that concerns our communities and society. This, I think, is what I would like to share. And then I would like to thank you for your attention, and sorry about the stops and coming back. But this is like this. Thank you very much. If you have some questions, I will be glad to answer.
Thank you so much, Oscar, for this very nice presentation and very interesting application. We have one question so far. It's, can you validate the results of ASIS with the Water Requirement Satisfaction Index, WRSI?
Look, yes, it's possible, but you see that the ASIS have an advantage. That is something in the past I used the water balance. However, you know that if the limitation of the number of the stations, if you are using some product like RFE or whatever other data or rainfall estimation like ECNWF, you need to test before to know the error that is in the estimation of rainfall. And then you can also compare, but always the resolution will be less in whatever of these products, because this will be at least 1 kilometer, and ECNWF or other products have high resolution, low resolution in this case.
Okay, thank you so much. We have another question, but maybe we can leave it for the discussion section, so we stick to the program. So, Jose?
Okay, thank you.
We cannot hear you, Jose.
Yes, I was saying that since we have 20 minutes at the end, maybe we can take some of the questions, yes, and we can move now to the second presentation. The second presentation will be given by Milan Fischer and will be about predictability of agricultural drought in a Pannonian Basin.
Hello, everyone. So my name is Milan Fischer. I'm from Global Change Research Institute of the Czech Republic Academy of Sciences. And I will be presenting today on behalf of the main author, Laura Crocetti. We are all part of the DRIPEN project consortium, which is composed from several institutes, which are listed here. And the main objective of the DRIPEN project is very similar to the main objective or the main title of this presentation, and that is predictability of agricultural drought in the Pannonian Basin. The Pannonian Basin is a part of the Danube Basin. Geographically, it is located in the area covering the whole Hungary, but also some neighboring countries like Czech Republic, Slovakia, Romania, Croatia, Austria, Serbia. And it is heavily agriculturally used area. It is a lowland. There is more than 70% of the agricultural land in the Pannonian Basin. The annual temperature is about 10.5 degrees Celsius, and the annual sum of precipitation is about 550 millimeters per year. Looking on the air temperature over the time, there is very obvious that there is some trend in the temperature. So temperature is showing increasing trend, almost 0.5 degrees per every 10 years. This is based on ERA 5 reanalysis, by the way. And if you look on the precipitation, there is no significant trend. Beside that, if we look on the reference evapotranspiration, which is representing the evaporative demand of the atmosphere, we can see a positive trend in reference evapotranspiration. If we are thinking that precipitation are remaining the same while evaporative demand of the atmosphere is increasing, it means that the aridity of the region is increasing and the probability of drought is increasing. Drought can be defined according to several classifications, but the most traditional is to divide drought into meteorological drought which is defined as a deficit of precipitation. So it means precipitation are lower than is usual in the given region. Then agricultural drought is defined usually as a soil moisture deficit, which is consequently causing vegetation stress and decline of the crop yields. At a more long-term basis, a drought can be defined as the decline, or can be identified by reduced stream flows, decline in groundwater levels, or decline in the availability of freshwater resources. And in this case, we are talking about so-called hydrological drought. All of these type of droughts are working on different timescales, and they are interconnected, and they are all they have all impacts on environment, economy, and society, and they are also leading to another drought classification, so-called socio-economic drought. If we look on the history of the drought in the Pannonian region over the last 60 years, we can see that there were several drought episodes, but the most important were in 1990, 2000, 2003, 2012, and 2015. We can later investigate on the presentation that each of these droughts has some differences in the precipitation distribution or temperature. Some of the droughts are more precipitation deficit driven, some of the droughts are more heat wave driven, some of the droughts are more like early season, some of those are more late season. But if you look on the spatial extent of these droughts, based on the standardized precipitation evapotranspiration index from ERA 5 reanalysis, we can also see that some of the droughts are more localized and some of the droughts are more widespread. For example, in 2003, this is an iconic drought which was which hit almost the whole Europe, all this domain like Pannonian Basin, but also West and Central Europe, Southeast Europe. On the other hand, in 2012, the drought was mainly in Pannonian region and southeast of the Europe. In 2015, the drought was mainly in northeast of the Europe, Central Europe, but not so much already in the Pannonian region. Drought in 2018 was very, let's say, very much reported, but it hit mainly the northwest and Central Europe, not so much the Pannonian region. Similar pictures can be obtained if we are looking on the evaporative stress index, which is based on the ratio of actual evapotranspiration to reference evapotranspiration determined from modest land surface observation. Again, we see the widespread drought 2003, Pannonian region drought in 2012, drought 2015 and 18. If we look on the drought impacts in the Pannonian Basin, which is here based on the study by Jakubinski et al., which was analyzing the reports in the media. In other words, mentioning about the droughts in the media. Again, we can see here the drought in 2003, 2007, 2015, 2018. Also, here is interesting, for example, drought in 2011, which was not so much identified by our Earth observation or ERA 5 reanalysis data. The main thing is that this drought was quite localized. It was mainly in Croatia, and there were a lot of reports about this drought. So these impacts are assessed for impacts in agriculture, forestry, and other parts. This slide is showing again some drought indices over the Pannonian region, mainly standardized precipitation index, evaporative stress index, and saltwater index. The last two are F observation based, while SPI is based on the ERA 5 analysis. Again, we can see identification of the drought in 2003, in 2007, 2012, and slightly also in 2015. On the maps on the right, we can see also the extent of the drought into spatial extent of the drought in 2012, which hit the whole Pannonian region. These were the, let's say, more meteorological drought indices. Now, if we look on other indices based on Earth observation, like NDVI index, vegetation optical depth index, and solar-induced chlorophyll anomalies indices, these are providing us information about the vegetation anomalies. And we can see here that we can observe or we can identify the drought in 2003, but not so much already the drought in 2007. We can again see the drought in 2012, but not so much the drought in 2015. By comparing with the previous slides, there is some kind of differences. And the main reason is that the meteorological drought, which is obtained from, for example, meteorological reanalysis or also other Earth observation data, is not necessarily leading to drought or to decline in vegetation, because it always depends when the drought is occurring. If the drought is occurring in the late part of the season, there is not already the effect on the vegetation. And that's why the meteorological drought is not always mirrored in the vegetation drought or agricultural drought. The main idea of the DryPan project, which is very related to this presentation, is to use numerical weather predictions and combine them with Earth observation data. These Earth observation data are either based on microwave satellites or optical satellites. Combine these three different data sets and use them within a machine learning framework or land surface modeling framework to predict or forecast the soil moisture conditions, vegetation conditions, or to predict and forecast the yields. We can use either numerical weather predictions individually and machine learning individually, or we can use either the combination of both. In my presentation, in the following slides, I will mainly focus on using machine learning to predict the yields. It's kind of example of the DryPan project rationale. Using the machine learning to predict the future state of the variables like drought or crop yields is based on the main hypothesis that drought and crop growth are highly autoregressive in nature. And both of these can be predicted from the initial to early signal in the predictors. I will present further the example of the yield predictions for the Pannonian region, where we used the data sets from the previous project Drydanube, where the data of yields were collected at the Nc2 level. You can see the levels, this map, the borders of these levels. In each country, they are a little bit different in size. We use further Earth observation predictors like vegetation indices, soil water index, and evaporative stress index. And using artificial neural network, we will try to predict the yield. Actually, we are trying to predict the final yields using data which are collected either only till April, which is April forecast, or data which are collected till May, which is May forecast, or data which are collected till June, which is the June forecast, or data which are collected till July, which is the July forecast. The assumption is that in July we have the most of the data collected, and the predictability of the yield should be the most accurate. We either used single predictors, like at this slide is shown, for example. We are using only enhanced vegetation index to try to predict the yields using the different forecasts, April, May, June, or July. Or we can combine different predictors, for example, enhanced vegetation index, evaporative stress index, and soil water index to predict the yields. In all cases, we are using 5 input layers for each predictor. So if we are using single predictor, there is only 5 inputs always, which are aggregated over the time. In April forecast, we have, for example, inputs from February, then from first half of March, second half of March, first half of April, and second half of April. while in the case of July forecast, we have aggregated together February and March, then the whole April, then the whole May, whole June, and whole July. Always just to have 5 predictors, because 5 inputs, because if you have a lot of inputs, there is a danger that the artificial neural network will be overtrained. We were testing always we were training the neural network on training data, which were represented by 2/3 of the data, and the 1/3 was left for validation. So here is the result of the using NDVI as a predictor and tested on the validation data. What we can see here that if we are using either April, May, June, or July forecast, there is almost no difference. So always the root mean square error is about 1 ton per hectare. And it's quite interesting that there is no improvement if we are approaching towards the harvest. On the other hand, if we are using enhanced vegetation index, the prediction is better, and in the same time, if we are approaching towards the harvest, we have more data and the prediction is improving. We also found that if we combine the enhanced vegetation index with other Earth observation data, either evaporative stress index or soil water index, the combination is leading to back in lower root mean square error. So combining these inputs is leading to better predictions. Finally, if we combine all 3, enhanced vegetation index, evaporative stress index, and soil water index, we are obtaining the best predictability. And we can again see that if we are approaching towards the harvest, the accuracy is increasing. This is also visible at this figure, the bar figure, which is showing the root mean square error for different artificial neural networks. For example, NDVI, we see no improvement when approaching towards the harvest, while EVI2 we see quite significant improvements when approaching toward the harvest. The same is valid for the combination of all 3 variables when we see that if we are approaching towards the harvest, the accuracy of predictions is better. But even in April already, we are at a better level of predictions than using just single predictors.
Excuse me, you have 2 minutes.
Okay. So by that, we can predict, by this approach, we can predict the yields. Here we can see the predictions for 2 contrasting years, 2012 and 2018. As I mentioned, 2012 was characterized by drought in the Pannonian region and southeast of the Europe, while 2018 was characterized by north-west drought. We can see that the yield decline in 2012 was predicted for this part where it was drought, but on the other hand, in 2018 there was no significant drought decline, which is in line with the previous slides and allocation of droughts. By this approach, we can also analyze the climatology of drought for different years. To conclude, the drought events were analyzed using a set of different Earth observation data. Each data set provides different context on drought. However, at the annual timescale, high convergence of droughts was determined, especially for the major drought like 2003-2012. Due to autoregressive nature of crop growth, we can predict the yields already early in the season using artificial neural networks. So I will thank you for your attention. I will also refer you to the manuscript which will be published in the Regional Environmental Change, written by Laura Crocetti. And the title is Earth Observation for Agricultural Drought and Monitoring in the Panoramian Basin. And most of this information presented here will be published in this paper. Thanks for your attention.
Thank you so much for this very complete work. I think it's a very interesting work, and you're covering plenty of options and indexes and so on. So I think it's a very good job. So far, I think we don't have any question. So maybe we can skip to the Oh yeah, sorry. One last last moment question. So, did you try using the individual bands instead of the vegetation indices?
Individual bands? Not at this moment. We just tried the existing products, let's say the existing available indices. But we are planning to try also different products, and we can also consider the individual bands. Thanks for the idea.
Okay, and another question we have: what type of ground measurements did you use for yield forecast to train, validate your ANN architecture?
So we used the yields which were collected in the national databases. These are the yields which are representing large area which is called Nc2 level. And in this case, we don't know exactly where is the position of the yield collection, which is producing some error in it. However, it's aggregated over some larger region, so this can somehow is masking these errors. We are also planning to try to predict the yields at the local levels, where we have the yields at the individual farms, and we have the remote sensing data at this individual farm. So we will see how it will work in this case, our test sites.
Okay, thank you so much.
Thank you.
Okay, thank you very much for the presentations so far, and also because we are perfectly on time, so we are doing well. So we can now move to the third presentation in the session, which is comparative evaluation of RadarSat-2 and Sentinel-1 data for estimation of weight logging score. And the presentation will be given by Sugandh Chauhan.
Thank you. I'll share the screen. Okay. Hello everyone. My name is Sugandh Chauhan, and I'm here to present a small section of my PhD research which concerns the assessment of crop lodging using remote sensing data. Here I'm going to share some results and insights about the utility of Sentinel-1 and RadarSat-2 data for the estimation of an index called lodging score. Let me first briefly explain what crop lodging is and how it can severely impact the crop development. In simple terms, crop lodging is the permanent bending of stems or displacement of the soil root system. For example, here you see a healthy crop which is standing upright, and here is an example of lodged crop, which is a problematic situation because it causes a lot of yield losses and deterioration of grain quality. It can be caused due to many factors which are genetic, management, or environmental factors. Therefore, timely assessment of this problem is required so that decisions related to expected crop yield, crop price, or its insurance can be made. Now, there are some traditional methods such as visual inspection to assess the lodging damage, but the problem with such methods is that they require on-site availability of a person, which is not always feasible. On the top of that, such visual measurements are point-based, subjective, time-consuming, and they can be even very costly. So in this regard, remote sensing technology providing information at high spatial and temporal resolution offers a promising alternative. Now, the lodging parameter that I'm focusing on in this presentation is the lodging score. Lodging score provides an assessment of how severe the lodging is. It is an index that comprises of two parameters. First one is the crop angle of inclination. It is the angle made by the crop stem from the vertical. And the second parameter is the extent of crop area that is lodged. For example, in this photo, we can see that this is the total area of the field that has been lodged, while this area is the healthy part. So an assessment of lodging score can help us predict the crop yield losses and can provide useful information for the extent of damage for the crop insurance companies as well. Now, based on the crop lodging score, I developed 4 classes of lodging severities. These are the 4 classes which are healthy, moderate, severe, and very severe. So for a healthy crop, the lodging score is almost 0, while for a very severely lodged crop, the lodging score can be up to 1. There are two main objectives of this presentation. The first one is to assess the utility of lodging score for detecting the time of lodging incidence using dense Sentinel-1 time series data. And secondly, the second objective is to investigate and compare the potential of multi-incidence angle radar set 2 and Sentinel-1 data to estimate crop lodging score and classify lodging severity. The study for this research was conducted in a very large agricultural farm called Bonifiche Ferraresi in northern Italy, where all the field measurements were made. This is a very big agricultural farm which produces a lot of crops such as wheat, barley, corn, rice, soybean, and potatoes. But my focus was primarily on wheat crop, which was sown in almost 600 hectares of the area in 2017 and 18 season. Wheat was sown in October 2017 and was harvested by the end of June 2018. And on this image, we can see that these are the sample plots which were considered for the field data collection, and they have been overlaid on the radar set 2 imagery. In terms of the data, we had two kinds of data sets. First is the Nc2 measurements. Now, to collect the Nc2 measurements, we selected almost 76 plots. Each plot was approximately 60 by 60 meters based on a stratified random sampling. The number of subplots within each plot was selected depending on the extent of lodged area. And each plot was visited 3 times between March to June 2018. And this is a list of in-situ measurements which were made. For example, the crop angle of inclination, plant height, leaf area index, biomass, soil moisture, etc. were measured. In terms of the satellite images, we acquired 5 multi-incidence angle radar set 2 images and 19 Sentinel-1 images. Here I would like to point out that for the first objective, which concerns detection of the time of lodging incidence, we have used the data across all these growth stages of wheat, and it corresponds to 19 Sentinel-1 images. While for the second objective, that concerns comparison of radar set 2 and Sentinel-1 data for estimating lodging score, we have focused on the later part of the growing season, which is from flowering stage onwards, because this is the time when the crop is very highly prone to lodging. This is the overall methodology of the study. In yellow, we see the satellite data inputs that were used for the study. In blue boxes, we see the important methodologies that were used to attain the objective. And in green, we see the important outputs. So there are 2 main outputs of this study. First is the detection of time of lodging incidence. For this, we used Sentinel-1 time series analysis. And the second main output of the research is lodging score. And for lodging score, we used both radar set 2 and Sentinel-1 data, and we developed a partial least square regression model. Now, from the lodging score, we also derived another output, which is called a classified lodging severity map. And this was developed for each data set. Coming to the results, this result shows the Sentinel-1 time series for different lodging severities and the ancillary rainfall and wind speed information. So we have 4 different classes of lodging severity, as I mentioned before, which is healthy, moderate, severe, and very severe. So the Sentinel-1 time series is shown with respect to the day of year. So on the x-axis, we have the day of the year, and on the y-axis, we have the VH backscatter, which is derived from Sentinel-1 data. On this slide, I'm only focusing on the VH backscatter and not on the other parameters, because we got the most significant results for VH backscatter. As you can see here, there is no distinct difference in the backscatter profile between the 4 classes until this point, which is until 120. But after 120, after 120, there is a significant increase in the backscatter of lodged wheat, which is observed at the flowering stage around the beginning of May. An interesting observation here is that in the first half here, where the VH backscatter for different classes do not change, but even though there is a constant increase in crop height, fresh mass and LAI. While in the second half here, lodging alone causes a distinct variation in the profiles. Therefore, we can say that using the Sentinel-1 dense time series data, it is possible to detect an approximate time when lodging happened in the field. And in this case, it is around this point, which is the DOY 120. And this correlates well with the field observations too. Secondly, we developed three partial least square regression models using the input from 3 satellite data sources, which is Sentinel-1, low incidence angle radar-set2, and high incidence angle radar-set2. We found that the low incidence angle radar-set2 data performed best in estimating the lodging score. We got the lowest RMSE in this case, which was 0.15, while the performance of Sentinel-1 and radar-set2 was almost comparable. Lastly, we applied the PLS models to 2 radar-set2 and 2 Sentinel-1 images to classify the lodging severity. In this case, this is the lodging severity map of low incidence angle radar-set2, of high incidence angle radar-set2, and this is the lodging severity map of low incidence angle radar-set2, while these two maps correspond to high incidence angle Sentinel-1 images. In this case, we made sure that the closest acquisition dates between radar-set2 and Sentinel-1 were selected, so that we could have a comparison between the results. In this case, the non-wheat areas have been masked out. So what we see here are only the wheat fields in the farm. The maps here indicate that lodging was quite widespread in the study site. All these yellow patches that we see in the maps, they are very severely lodged wheat, while the blue one is a perfectly healthy crop. So we can see that from May to June, there is a progression of lodging as the yellow area is increasing, while the dark blue area is decreasing. And it also makes sense because as the crop approaches maturity, which is around June, the plant is also more susceptible to lodging. So here are the main conclusions of the research. Firstly, from the review of literature, we found that the existing information on lodging is very limited, which makes it very difficult to address this very important yield limiting factor. Therefore, this study is the first attempt to demonstrate the feasibility of SAR remote sensing data for detecting the time of lodging incidence and estimating crop lodging score and classify lodging severity. In terms of the detection of time of lodging incidence, the Sentinel-1 derived VH backscatter proved to be the most useful parameter, as it could easily discriminate between different lodging severity classes, and we could also detect the time of lodging incidence around DOY 121. In the second case, the low incidence angle radar-set2 data performed best among all the 3 models for estimating lodging score and classifying lodging severity. But we would also like to emphasize here that the results obtained from Sentinel-1 time series data are equally useful in this regard, especially if you want to develop operational applications for lodging monitoring in almost real time in the future. The use of Sentinel-1 data will be very useful. In this case, Sentinel-1 data could explain around 65% of the variability in lodging score, which is also quite high. And lastly, I would like to conclude that these results are important in the context of operational crop lodging assessment in particular, and sustainable agriculture in general. Thank you.
Thank you so much for this very interesting study and I think it's very innovative study. So we have plenty of time for questions, so I encourage the audience to send questions. We have one so far. It says, very interesting work. Was there any relation between optical image LAI and the microwave image lodging score in relation with crop stages of the crop?
Okay. So this study primarily focused on only using synthetic aperture radar data. We did not focus on Sentinel-2 for the LAI estimation, but in a separate study, we also tried to use the Sentinel-2 time series data for detecting the time of lodging incidents. And we could see that the ultimate conclusion was that if we combine Sentinel-1 and Sentinel-2 data together, it is possible to define even more accurate window of when lodging happened in the field.
Perfect. And there's another question. How about quantifying the area affected by lodging using Sentinel-1?
So the lodging score that we have tried to estimate here is, it is a parameter which also includes lodged area. So from the map, from the lodging severity maps which I just showed, it is possible to delineate the amount of lodged area as well.
Okay. I saw also some, like, there's no other question, so I just wanna, I saw also some differences between RadarSat and Sentinel-2. It looked like RadarSat had some noise that you couldn't see with Sentinel-1.
Actually, yeah, it is possible that there is some noise in RadarSat too. Also, the spatial resolution is higher. But the thing with the lodging is, it happens very, the distribution of lodging is very random.
Okay.
So we can see a very small patch, which is like 5 by 5 meters, where there is a lodging, and we can see a very large patch as big as 30 by 30 meters. So it's like difficult to say if it's actually noise or it is lodging. Because lodging can also happen in very distributed spots, which looks like it is noise.
And there's also the problem of quantifying the area because it's very scattered.
Yes.
And maybe hard to validate as well, right?
Yes, it is.
Okay, so I think we don't have any further question. Maybe we should switch to the next presenter.
Thank you.
Thank you.
Okay, thank you for your presentation. Then we will move to the next speaker, which will change the topic. And now we will talk about towards the development of fluorescence-based photosynthesis estimates for vegetation productivity monitoring from space, 2 years of CentiFlex activities. And the presentation will be given by Johan Barrels. Please, Johan.
Hello, can you hear me now?
Yes, we can hear you now.
Okay, so good afternoon, everyone. Thanks a lot for giving me the opportunity to give this talk. I will give an overview of a 5-year project so-called CentiFlex. And this project is done by me together with a whole team of young researchers and a few postdocs. Let me start with, if I move forward, I apologize. So I will stop sharing. That doesn't look good. And I will share again. Let me see. Since the next slide is not appearing, I will stop sharing again and try to I apologize. So I share again. Can you see my screen now? I guess so. And let me Okay. Like this, it works, right? So I apologize, so I'm not using the full screen anymore. And I want to start with just a general question, how to quantify terrestrial photosynthetic activity. From a satellite point of view, like Sentinel-3, this is typically done with optical data, where we try to measure vegetation. And of course, and surface is never only vegetation. It's also there's also soil background, and it's also not photosynthetic activity, because at the end, optical sensor only measure the greenness, and we don't know what's going on in the plants. So since 2016, ESA approved a radical new approach, which is the FLEX mission. And the FLEX mission aims to quantify a signal that comes directly from the vegetation itself, namely fluorescence. And fluorescence, interesting enough, is directly also related to the photosynthetic activity. So in this way, we would have a direct link to see what's going on in the plants. We can measure actual photosynthesis. Now, what is fluorescence? It's a very small signal that you cannot see with your naked eye, but it exists, and you can easily observe it in the laboratory, as you can see in the top left figure. This is so small figure that is directly related to photosynthesis. It's actually a byproduct, but by measuring fluorescence and having information about the plant, we can in this way track back to go and have knowledge about the photosynthetic activity. Interesting enough, this fluorescence signal is not just one band, as we often see, but actually it's a broad signal ranging from 650 nanometer all the way to 800 nanometer. It has these two specific peaks, and these changes in these peaks also can give us information about the status of the plant. Unfortunately, it's a very complex process. It's a very small signal. Not only that, also there occurs scattering and reabsorbing both at the leaf scale, canopy scale, and eventually the canopies, the atmosphere scale. So for this, the FLEX mission will fly in tandem with Sentinel-3 in order to make use of both combination of data. And the main objective of FLEX is to quantify actual photosynthetic activity of terrestrial ecosystems from space, accounting for vegetation health status and stress conditions. Where are we now? Well, fluorescence is long known, and for the last 30 years at leaf and with physiology level, there's a lot of known. Also, more and more, studies start to be done at the canopy scale, even with airborne sensors to the airborne scale. But we're moving towards space. It's still a more unexplored area. And that's why we try to fit in with the FLEX mission and with this project. So it brings us to the main objectives of the project is to start practical, to develop a prototype vegetation productivity monitoring facility from forthcoming FLEX and Sentinel-3 satellite observations. There are two main questions. The first one is to try to understand and disentangle the different mechanisms that are taking place with the fluorescence signal moving towards photosynthesis. And having better understood these mechanisms, a second, more practical objective is to build a FLEX Sentinel-3 vegetation productivity monitoring facility based on assimilation of the most important variables. And in fact, this project goes very close in hands together with ESA, because ESA also has a lot of projects ongoing, more on the raw data processing and converting that into essential products such as vegetation products and the fluorescence. With this project, we try to move further towards so-called higher level products and assimilate the key variables into eventually that we can quantify photosynthetic activity. Now, the project consists of 6 main tasks. The first 3 mainly cover the first objective, the second 3 cover the second objective. So, of course, the first task is about data generation, and then we start to retrieve fluorescence and vegetation properties. In task 3 is supposed to do the assimilation. That is still under construction. While in task 4, we try to develop this vegetation productivity facility. We take also the spatio-temporal aspect into account in task 5. And at the end, since we work for Europe, for Brussels, we are supposed to deliver impact. In task 6, we develop applications that can be used for the whole community. Task 1 data is simple, so it's Sentinel-3, but we also have support from Sentinel-2, Sentinel-1. We have campaign data, and also we make use of physical models, radiative transfer models. Task 2 is already more interesting, because here in this task we work on the fluorescence retrieval on one hand and vegetation properties retrieval on the other hand. Now, fluorescence retrieval became very big for the last 10 years and can be ranging from very simple vegetation indices methods until advanced inversion methods of relative transfer models. But what is sure is that it's a difficult task, and also it requires quite some optimization or tuning, making that it's not yet so well consolidated what would be the best performing method for instance, for flex. So because so many methods and uncertainties are present there, we felt that there was tools were lacking how to systematically compare and analyze these different methods. And for that reason, we developed a toolbox where all the state-of-the-art methods are implemented, and it allows the user to play and to compare the different methods and see what is the performance. On the other hand, vegetation properties retrieval is much more consolidated, and we make use of the same kind of approaches as has been done in earlier missions. Basically, we train a machine learning algorithm in this way so that it retrieves vegetation properties such as chlorophyll, LAI, fractional cover, FFR. The novelties here, however, is that we make use not of neural networks, but rather of Gaussian processes, because that also gives us directly uncertainties, and we train it with the scope model in order to keep consistency with fluorescence retrieval. So here we see an example of maps from the products that we retrieved. By now the algorithms are pretty operational. We can apply to anywhere in the world, and it immediately gives us chlorophyll, LAI, FFR, F-cover. Not only that, but also with associated uncertainties, so we can see per pixel how well the algorithm is performing. We also did a validation against the official Sentinel-3 products, OTCI, the Ortschi Threshold Chlorophyll Index, and the OGVI, the Ortschi Global Vegetation Index, which is like FFR. And you can see the consistency of our products against the official Sentinel-3 products. Moreover, the chlorophyll index is just an index, so you cannot quantify that into the field. Meanwhile, once you really quantify chlorophyll, this you can validate into the field. We started processing some Sentinel-3 time series back in 2018 when the first data came available. We decided to move to Southern Hemisphere, to Argentina, because from October onward, so that we can see some phenology, and you can see in these maps that we can quantify the changes over time. We're moving towards vegetation productivity monitoring facility. However, then the key question is how to make it smooth, how to make it run fast. So for models that are trained with machine learning, that's no problem. They deliver products immediately. However, the more complex retrieval methods, such as the fluorescence retrieval method, is much more challenging. And for this, we were searching for ways how to speed up these processes. We were quite innovative in developing so-called emulation methods, and those are statistical methods that are able to approximate the functioning of original physical methods such as RTMs. In this case here, in this blue square, you can see an example how advanced RTM scope model, we can approximate that and deliver the same kind of output with the emulator, but way faster. This is very interesting because once you have such a statistical model available, you can run it over anywhere. And on the right, you see a small example that we used a Sentinel-2 image for the spatial texture. We run an emulator that gave hyperspectral output over it. So in this way, we can reconstruct Sentinel-2-like images, but hyperspectral. And why is this of interest? Because when moving towards fluorescence retrieval, then this starts to become really interesting. Fluorescence retrieval, the way it's done nowadays, it's done on supercomputers. It takes hours and hours of time from the radiance data. So we use that data as starting point. We developed an emulator in the way that just from the same raw input data, radiance data, we have a model developed, and it reconstructs the same kind of fluorescence output as the original retrieval algorithm. And why is this of interest? It speeds up tremendously. Now we generate the same kind of maps within a minute, and you can see they are pretty much the same. Of course, an emulator will always perform only as good as the original model. But once we have a model, an emulator developed that provides exactly the same kind of output as the original model, it opens all kinds of opportunities to speed up processing and providing the same accuracy or quality of products. Moving towards task number 5, this we have elaborated most and is about integrating spatio-temporal methods. We're moving towards time series. Also here, loads of methods exist. However, so far the machine learning methods have not really too much introduced into it. For instance, these time series products hardly provide uncertainties. And also here, because of all these methods, a systematic comparison and optimization is required. And the same is for phenology indicator estimated. Lots of methods exist, but comparison is lacking. So we developed also here a user-friendly GUI toolbox so that you can test different kind of data methods and see and compare and see what's best performing. It's called Daytimes. It has 3 main tools in it, modules. So gap filling, since data is often noisy and there are gaps due to clouds. Second, vegetation phenological characteristics, such as start of season, end of season. And finally, we are even able to fuse different types of time series data sources. It's really well developed, I would say, and user-friendly. You can run it with all kind of input data, just single observations, like a single pixel, or complete images. And you have nice outputs, such as creation of animations or interpolation. But more importantly, why we do so? Because with optical data, there's always a problem of clouds, and that's what you see on the left. And what you want to have is on the right. You want to have maps of your vegetation products without any influence of clouds or any kind of other noise or gaps. The toolbox allows you to reconstruct products such as leaf area index, for instance, for every 10 days or so, or you can choose your own dates, or you can decide it just fills up the gaps due to clouds and you keep the original values. The key or the most novelty of this toolbox is that we don't only use of the classical time series methods, but we also introduced a large amount of machine learning methods, and you can immediately compare them and see what is best performing to do the fitting over time. So in this way, you get smoother data without any clouds. You can even get uncertainties if you wish, and you can see which one is best performing. This also can then be used for phenology indicators estimations, such as start of season, end of season, the day when the maximum value appeared or the maximum value. And since that the toolbox allowed to select your own region of interest, so you can do it with masks and do these phenology calculations for crop specific. In this way, you can see for multiple seasons when the season starts and ends and so on. Perhaps most exciting is also to make use of fusion of multiple satellite data, such as Sentinel, such as radar data, together with LAI from the Sentinel-2 optical data. And we worked further on this on these Gaussian processes. There exists this multi-output version, which allows to fuse and make use of the complementary or the shared data in order that you can come to better estimations. And this I would like to exemplify a little bit when we see on top Sentinel-2 LAI observations, which has a lot of missing values due to clouds. Those are these red points at the bottom of the figure. And on the other hand, there is the Sentinel-1 fusion, which is much more regular and you have much more data available. The multi-output GPR fuses both data, gives you the uncertainties, and in this way you can get observations on exactly the same points as either in Sentinel-2 or Sentinel-1 observation is available. Maybe from this graph, it is not that impressive because actually just the Sentinel-2 data alone, it's quite smooth and the interpolation works pretty well. But we worked further on it and we decided to create large gaps. So we removed several points. So actually that you miss the growing season if you would make use of only optical data. Because we make use, and that's here, you can see that here in the top figure. When you have just optical data and we use only Gaussian processes for the time series processing, it will completely miss the growing season. And this is the best you can do with only optical data. However, when you make also use of the Sentinel-1, so the radar data that is able to detect these trends in the growing season, you can see then it manages to predict correctly the growing season with a peak somewhere in June. And so this gives us a very powerful tool to fuse different types of data that can be either complementary, but also both can be optical. And this is, to me, a very interesting figure because we plotted well, starting from now, the Sentinel-2 NDVI points, and we went further back in time with Landsat 8, Landsat 7, all the way back to the 80s to Landsat 5. And when you apply then your fusing method, you can basically reconstruct your Sentinel-2 or your Landsat 8 all the way back to the 80s. So it means that if there is any wish for, we could develop Sentinel-2-like products that go back, that are given observations from the 80s. Or the other way around, if you wish, you can have your Landsat 5 products that we are recording in the 80s. We can continue with the trend all the way up to now. So it allows us to move back to the past and see how patterns were occurring with the same type of data. And this is especially of interest for the Sentiflex project because Sentinel-3 will fly together in tandem with Flex, but Sentinel-3 provides much more regularly our products, such as our vegetation products, than Flex because of the more narrow swath. By making use of this fusion method, we could provide also Flex-like products at the temporal resolution of Sentinel-3.
Excuse me, Johan, you have 2 minutes.
Yes, sure, it's fine. Now, this is all very computationally demanding, and also all this data is not just available on our computer. To do so, we had to find with more efficient solution, and that's how we discovered Google Earth Engine. And nowadays, we try to do our processing directly into Google Earth Engine, which gives us a complete new world of options. For instance, we can plug in our vegetation models for Sentinel-2 and immediately map whole Europe, as you can see here, or even the whole world at a spatial resolution of 20 meters. So this is the LAI product. And by also including the gap-filling methods that was earlier explained, we can provide maps of, for instance, here, whole Spain at a resolution of 20 meters without any clouds. This is a lot of processing, but it's possible to do this for the whole world or to do time series, so to see how LAI is evolving here over the Iberian Peninsula. Finally, we also are supposed to deliver some impact. The work here is for the benefit of the community. So all the methods that we develop, we also implemented into toolboxes that are freely available to the community so that other people also can further develop or make use of these methods here developed. So in a nutshell, the current status of the Sentiflex, I believe we have the tools in hand to generate products of adjacent vegetation properties. We have the tools to optimize fluorescence retrieval and even accelerate it by means of the emulation methods. We can do time series, gap filling, philology calculation, and even fuse multi-sensor time series data. Finally, we even are operational into Google Earth Engine so that eventually we can do this processing at a European scale. What is the perspectives for the next coming 2 years is to combine these different products into an assimilation scheme. This is still lacking, and eventually try to upscale these methods at the European level. So altogether, eventually that we are prepared for when Flex is launched by 2024. And that's my presentation. Thanks a lot.
Thank you very much, Johan. Very interesting and complex but ambitious project that you presented. I'm eager to see and use this Flex data hopefully into 2024. Let's see. So we have 2 questions so far. Are the retrieval image based? Are the retrievals image based? Do you use previous retrievals as prior information for the current retrieval? I think it's regarding the gap filling method.
Yeah. So the gap filling method is actually nothing more than training of a machine learning algorithm, but rather than training by spectra or so, you train into the temporal domain. So you use the points that you have available, you train that, and that allows you to do the estimation for the missing points. So that can be done pixel by pixel each time you retrain, or you can also make a general model that is more generic, maybe not that specialized, but more robust, and you can then apply that immediately to the whole image.
Yeah, Johan, you have your camera off. Can you please turn it on? Maybe when you stop sharing the screen.
Yes. Here it
Okay,
is.
so the second question, will the daytimes code become available also as command line interface functionality or even Python code for easy ingestion or in existing pipelines?
Yes, thanks, Christoph, for this question. So the daytimes software is freely available, and it's a standalone software. No MATLAB or any other language is required. However, when it comes to the source code, that will not immediately become available. But as I said, we try to move towards Google Earth Engine, of one of these methods, and eventually these codes should become available into the Google Earth Engine framework.
Okay, and the last question, amazing work. What do you think might be the potentials of CubeSats with limited spectral resolution to fill in the gaps of low temporal resolution Sentinel-2?
Yes, it's perfectly possible. No, so with this fusion approach, it really doesn't matter what is the data source as long as it can be complementary to each other, as we saw with the different type of Landsat and Sentinel-2 or Sentinel-2 with Sentinel-1. So if we share the same kind of information, for instance, if there are other NDVI or radar index what also provide the same kind of patterns, then we can talk about fusion, that they can be complementary to each other. So as long as the data is kind of the same, we can perfectly fuse it. Perfect.
So Christoph is again asking if you're considering the implementation out of Google Earth Engine as well, like on DIAS, OpenEO, or Euro Data Cube.
Yes, probably not. so we are scientists, no, we are academics, so we develop new methods, but we are not really responsible for operational approaches. We are very welcome to collaborate, that other people implement these into more operational platforms. But for us, the main interest is the development of the methods.
Okay, we have one last question, but maybe we can keep it for the discussion section, so we can go to the next presenter.
Okay. Thanks a lot.
Yes, I think we can move now to the last presentation in the session. But remember that later on we will have additional 20 minutes discussion, and then after that 1 hour requirement booth discussion as well. So now we move to the last presentation. That is a high-level scientific support action for the agricultural sector by EU4Agri, the insurance showcase. The presentation will be given by David Kolitsus.
So thank you. So I'm sharing my screen right now. Let me know if that works. Yes, I just assume that it works. Yeah, thank you very much for having me. My name is David Kolitsus. I work at Geo. We are an SME based in Innsbruck, Austria. And well, I'm really pleased to be here, and actually I want to thank all the speakers before me, because I actually can connect to pretty much each topic that we've seen so far, because this talk will be a bit different. It's a bit more on a higher level, not only trying to find scientific requirements, but actually draw a big picture on what are the requirements on agriculture in the whole, what stakeholder groups are there, what are their requirements, and what are the gaps and challenges they are finding. And specifically all the research we have seen, the last talks are actually pinpointing down individual gaps and problems we have seen. So whether it's lodging for hail damage or whether it's data fusion. So all of this come together, and I try to give this a bit comprehensive, quite not generic, but high level talk. And I try to see where everything fits together, so that we're not only doing some research, but actually we fill needs of different stakeholder groups, and that we make the best of our effort and really provide decision makers, or actually also businesses with solutions they can work with and create value to different stakeholders. And how I'm doing this, actually, I'm combining the effort of two different activities, mainly two projects, which are from different sources. So one is EU4Agri. It's quite similar to the name of this conference, so it's quite nice for me to be here. It's a European Commission support project, and the subtitle is Bringing Together the Knowledge for Better Agriculture Monitoring. So this covers, of course, a wide range of applications and different representatives and stakeholders involved. But we're combining this. We think the subtitle is the insurance showcase, is that we also have an ESA activity at Geo, which is the EO4I project. So it's a best practice ESA project, Earth observation for the agro-insurance sector. So one stakeholder groups agro-insurance companies, what are their needs in Earth observation data products, and what gaps, what do they see missing? So where do they see a lack of support from the Earth observation community? So before going into details, let's rate what are the two components, EU4Agri on the left-hand side, European Commission project, 2 years close to the end, and it's quite a widespread consortium, really going from SMEs over research institutes, but also national paying agencies, so that we have not only part of the agriculture, because agriculture covers a huge amount of different involved players, so we have all stakeholder groups on board. Whereas the EO4I is really a best practice study from ESA, and the objective is to get a roadmap for the development of guidelines, of technical and scientific guidelines, so that this sector, the agro-insurance sector, can make better use of Earth observation data and see what are the capabilities already and what are the geo information that we actually need. So, and there, of course, we see gaps and can make scientific recommendations, what are research topics that at least this sector requires and would see a benefit in their daily life. So that I have these two separated, and I will switch a bit between those two because, yeah, you will see the story. So starting with EU4Agri, which I'm representing, you can see the consortium is widespread over Europe, and we're really trying to cover each part of the value-adding chain. So just coming from EU data providers like EGEOS in Italy, we have research in academia and Scrum of Crow from Belgium. I know that also some partners are in this call right now, so greetings to you. We also have various SMEs like GeoWorld, what I'm representing, but also the National Paying Agency of Lithuania. For example, what is the need of the Common Agriculture Policy, so by this paying agency? So really try to take the whole pictures of involved players, involved stakeholder groups, and their interest into Earth observation-based agriculture systems. This all is a coordination and support action under European Commission grant. So what are the objectives? So these are the overall objectives, but let me just highlight those which are relevant to this part, because I cannot cover the whole activity. So objective 2 is the identification of potential end user groups. So at the end, all products in development we are happy if we find someone who actually has a need for that and finds a value that is given to him with the outcome of the analysis. And the agri-food sector, public sector, the food security sector, some of them are mentioned. But here's also the overlap or the common interest between the EO4Agri and this EO4I, the Earth observation for agri-insurance. So you want to directly connect and work together with the different stakeholder groups. And here we found the perfect solution that the ESA best practice already had this idea in mind that they are directly working together with the insurances. So they do the whole assessment of requirements. They have this very active approach of meeting and gathering requirements, not from an EU perspective, but actually from a end user's point of view. What are their needs and where do they need them? When do they need it in time, etc. And we can see actually that these different stakeholder groups, so agri-food industry, but also financial sector, food security, although having different objectives, we have a similar need for various EU-based products in terms of the EU product, whether it's a crop type map, an indication of crop damage, whether it's food security. So what you see before, there are different end users for various similar products. So what we can do and have done is to develop scientific and technical guidelines which do not only serve one stakeholder group, but actually are a common interest of these different sectors, which might not be aware of that they have similar interests. So there's quite an overlap in needs, but also in problems and challenges they are facing with the data, whether it's data quality, is it gaps in the time series, just as Joachim had mentioned, the data fusion, which is of interest to pretty much all users to some degree. But there are also other points like the ICT support. So at the end, you need to have large processing chains. So also you need to run it somewhere. So we also have two providers which are running one of the DIASes, so one of the data information and access system, one of the IT infrastructure where you can run all this analysis. So we not only have this scientific research, but also the application level in mind. At the end, this must be run somewhere, it must be fast, it must be cost effective at the end. So we are creating scientific, technical, and economic guidelines for these different sectors, and have seen quite an overlap in interests and also in challenges. The other objectives is very high level, is a policy review, because sometimes it's policy recommendation that is the most beneficial. It's not a scientific problem that they're challenging, but rather it's an eligibility problem that the data might not be used in certain use cases. So this is more on a high level that we try to identify this. So the EU data may be satisfying from a technical point of view, but it might be another blocking, limiting factor, which is was identified. And yeah, I think this what I want to highlight is that we created and and drafted a close to finalize a strategic research agenda. So from each of the stakeholder groups, we combined the problems, the challenges, the gaps, and the research needs into one common strategic research agenda. And this, unfortunately, I cannot share it right now because it has not been approved, but it will be approved in the next couple of weeks. So very soon, this is an outcome that I'm very happy to share with the whole community. So how does the EOFRAG work? So this is on the up end, so the green ones are like the low-level engagement process with the different stakeholder groups, directly talking to various organizations, research institutes, insurance companies, banks, sector, etc., also the public agencies. And the tools we're having for that is then to come up with a cooperation framework, this policy roadmap, but as a highlight here for today's talk, the strategic research agenda. And all at the end, we have a white paper which addresses this on a high level, try to push from the lower level end user needs towards a higher audience and to the policy makers. So yeah, as I said, one of the stakeholders is best represented by this Earth observation best practice for agro-insurance. This is a project led by Geo, but I'm also happy to mention the partners Vito and CGI. And we have 3 different insurance companies on board, which is Swisshail from Switzerland, Vereinigte Hagel in Germany, and Austrian Health. So 3 European-wide, more or less, working insurance companies in the agro business. And what are the objectives of this one is, it was a bit more than 2-year project. So in the first year, it was really about the geo information need of this sector. What are the products, the geo information that they need in their business process? So because they have a business, so they need to operate that and they need support. And they see a big opportunity with EO data. I think they have, well, been addressed for 20 years that Earth observation data can help them. I think now we are really at a point they're very active and very much involved and very open and see a big added value from Earth observation, from freely available Earth observation data. And 2020, we can see what are the capabilities from the Earth observation side already, and what are the existing gaps. And the final set is a roadmap for the guideline development to see that EO data is not only used for scientific studies, but is used in the business chain of these insurances for the next years to come. Because if they apply in the business chain, they're talking about 10 years of implementing this. It's not an easy way forward for them. If you try to understand the user needs, you actually need to, in this case, talk about the business processes. So in agro-insurance case, these are 5 different subdomains that you have, whether it's on the product development, but you also have underwriting, claim settlements, loss adjustment, or the production. So each of them they've identified challenges, and each of them, they saw a potential for Earth observation data to provide. So overall, there were like 61 challenges identified, but you must keep in mind that there is an EO-related component of it, but it always only works if you also take into account the non-EO-related challenge on top. So to have a complete picture of how are they going to use it, how do they want to use it, is a big way more than just having an EO product at the right time, but it needs to be within each business at the right non-EO related data or requirement they have on top. So very often, if you talk about GPS locations, so GNSS activities as well. So only, let's say, single individual Earth observation satellite 2, Sentinel-2 vegetation series is not enough for them. So they have additional requirements that need to be fulfilled. And of course, they're looking into what's happening in the next generation. So we already see that the FLEX mission is mentioned here. So very happy that the activities, like Joachim just mentioned before, are already well aware, well advanced, and that they look into a bright future. And many of the problems we are having now, or gaps we have seen now, will be closed by activities such as we have seen before. From this 61 challenges, what we have really done is like a list of Geo Information Requirements. So and many of them have actually been mentioned during the session today, whether it's on crop type, whether it's on crop vegetation monitoring and stress indication. Yield monitoring was mentioned, but also the lodging, which is a bit new. It's not, let's say, it's not on the TRL of 9. So I'm very happy that most of the things and research we have seen today actually already finds its way into a geo information requirement, which is stated and validated from the stakeholder group. So there are many tables like this, seeing they have this need, and they yeah, interested in having this, and they see a value in it. But that is also come when we go the analysis that there's a gap. So for each of these products, there will be a report available with given gaps. And as you can see, for many, we already see for example, that the FLEX mission might be a problem to solve this. And I'm really looking forward to more results seeing that. So here I can really not go into detail, just say that the high level activity that is happening. So we have a validated, not one, but various stakeholder groups requirements. We see some gaps, and we see many of them addressed in the most recent scientific research, and we really appreciate that. And at the end, what at least with the insurance companies came up with is a list of requirements, and also what scale do we need it, and what is the business importance to them, so then you can make a ranking. So yield estimation is kind of the holy grail that you want to have. So the highest importance from business importance, whereas the technical readiness is still considered to be on a level of 1 to 5. The same goes actually there for soil moisture. We have a group here. So as you can see, for various requirements, we have heard already a presentation today. For example, soil moisture, I'd like to mention that actually for soil moisture, there might be various requirements. So one on a parcel level, whereas also soil moisture only on a regional level would be beneficial for those companies. So you can see that one EO product might serve different purposes depending on the scale that you're working on.
Excuse me, David, you have 2 minutes.
Perfect. Make it okay. So this was the agro-insurance, and we did the same for 3 to 4 different stakeholder groups, and I will just, let's say, give a high-level overview. So we can see that different stakeholder groups have the same need. For example, we identified a golden group of user requirements, and actually one of them, which I wasn't aware of, is actually weather forecast data. So even though we are looking to satellite data, for optical radar, as an active passive monitoring, but as a weather forecast is still one of the biggest nominator where we needed improvement. And also the drought early warning system, as we've seen before, is of high interest. What we did then is a kind of a scientific analysis case study. So we did for each of these use cases, we did a review of the most recent literature. So we make an overview of what are the latest publications on that. So we created, and I will jump a bit now, something which we call a knowledge hub. This is an activity together with Geo, with the group on Earth observation. They started identifying that there's a need for better sharing of information and knowledge. So there's a knowledge hub on Geo, and we as Geo for Agri Consortium derived so far like 20 entries in this knowledge hub. It's not yet on Geo, but we are in contact with them, which is a combination of scientific literature, of related projects and success stories, something which we can share with them, and further enriching the whole community, which is quite scattered in the case of agriculture. So this is my second, I think my last slide already. So although I cannot share the scientific use agenda by today because we need to wait until its approval, we have discussed it on several occasions with several DGs. I think many of the audience, many of these DG representatives might also be part of the audience of today. We had a very intense discussion and we'll publish it soon. So I have the links in the document, you can find them there. I'm very happy to share them afterwards as well. And the same goes for the best practice for agro-insurance ESA activity. This roadmap will be published very soon. And these are two out of many outcomes of these projects which you can bring into the discussion of where the research needs to go in order to have meaningful applications where we create something of added value to these different stakeholder groups. And by that, I want to thank and just if you have questions, whether now, but you can also directly contact me via email. And thank you. And looking forward to questions, discussion, whatever.
Thanks so much, David. Very nice project and very interesting link with the insurance companies and their needs. So I think it's very good for us scientists and also for the space agencies to see which are their needs. So I think it's very interesting so far. So we don't have any questions so far. We are almost there into the discussion time, so I don't know, maybe we can wait a little to see if there's any question that pops up during the discussion section. And I encourage everyone in the audience to send further questions during these 20 minutes left that we have for this session. Jose, do you want to give a highlights of the session?
Yes, well, while we are waiting for more questions for all the speakers during this session, and we will collect the question and then go back to some of the questions to you. Basically, the idea now for this 20 minutes discussion is not just maybe go to a specific detailed questions to each one of the presentations, but also to address some more general questions about the topic of the session today, and to see if we have really covered all the different issues that we were supposed to cover in this particular session. And the title of the session was Climate Adaptation. And the idea was to collect things like, for instance, how to monitor stresses. So by using either direct remote sensing techniques, either optical or radar or combinations, or by using some indices combining remote sensing data with meteorological data, with ground data, to came to a way of monitoring the stresses, to identify the stresses in vegetation, basically. The other topic that was proposed in the context of the content of the session was the impact of changing climate. Basically, we will have a situation where we are changing the growing conditions in vegetation, so either by increasing the ambient temperature, or by increasing the length of the growing season, or changing the conditions in which vegetation has to grow. And we also are increasing the capability of the systems of string events. So basically, we will go more into situations which are in the two extremes of the situations. And now, how to monitor these cases, how to make a risk assessment of how vegetation productivity and agriculture in general will be affected by these climate changes in the environmental conditions. The other point that was also somehow included in the discussion was how to combine the capability to forecast the effects of this risk, or basically to be able to predict maybe droughts, floods, heat waves, versus the capability of monitoring the damage caused by those things. Because these two aspects are being in the presentation somehow. So one thing is to see the capability we can predict or at least advance what will be the consequences. But on the other hand, there is a need also for the insurance companies to know after the event has taken place, what are the consequences, what are the damage. And the last point I would like to bring for the discussion, because it was also in the preparation of this session, one of the topics we want to address is the issue about particular test cases. So we are addressing applications in some specific test sites, addressing a specific methodology that probably is adapted to this particular site, versus the capability to develop algorithms which are in principle applicable everywhere in a consistent manner. So I think all these topics have been in the presentations. So right now what we want is to address specific questions for the speakers, but also some more general questions about this EU for agriculture in the context of climate change and climate adaptations. So I think we have now more questions. Maybe, Belen, can you go through the new questions?
Yeah, there's one. Can you use this model and parameter for aquatic agriculture crops for better water management? I'm not sure to whom this question is addressed.
It's Sugandh. It's Sugandh.
Okay. Are you there? I think we lost her.
Yeah, I think we have lost. Is somebody else ready to answer?
Will you repeat the question, please?
Yeah, sure. Can you use this model and parameter for aquatic agriculture crops for better water management? I guess that it's also related to droughts. Well, drought, no. If it's aquatic, then there's no drought.
I think it was for the lodging.
Yeah, it should be lodging. Okay, so maybe we can continue with the discussion until maybe.
I think there were some questions before that were not addressed to the speaker.
Yeah, sure.
So maybe.
Sure, there was one for Oscar that we left for the end. So thank you for the presentation. Is there any future work or real-time crop monitoring with the probabilities that you are gained through the historical data that you have gained? Oscar? Yeah.
Yes, thank you. What is us is really operational in this moment. What I present, everything is operational. One is a global level. Then you can visit all the outputs for the whole globe every 10 days and the use Earth observation website. And the country level ASIS, the next generation ASIS, is applied in some countries in Central America, like Nicaragua, Honduras, El Salvador. They're going to have his own website automatically next week. At this moment, they are also Mexico. And we have a proposal to implement, now that we have the full package operational, to Africa. We would like we have a proposal, but we are looking for funds and partnership to implement in Africa. There are some of the applications that still didn't test, like how to apply it to crop assurance. It's very practical because they reduce the basic risk because it's automatic, and then nobody can modify the outputs, but it's not yet tested. It is something that we are moving to the operational and applications. Then we are welcome if someone wants to join to us to support countries. Thank you.
Thanks. Okay, so we don't have further questions, so I think it's interesting to go on with what Jose was suggesting. I think there were very interesting questions that raised, like if we are ready maybe to go in more like predicting that there's going to be any damage to the crop before it actually happens. We saw some results in these previous presentations that are encouraging, so maybe a good question and in line with the GeoGlam mandate, like trying to quantify all these impacts. What's your view? We can talk maybe within the speakers of this session, like what's your vision on this?
Could I start with a question on that? Because one of the findings we had and the discussion is really on in situ data. So there are many use cases and it's nice scientific studies on very specific areas with excellent results and very promising. And as soon as we try to scale this up, there are no connections more to get in situ data. So there are some activities like the JCAM, so a Geo supported joint experiment for crop assessment and monitoring, which has some sites all over the world. But to be honest, as soon as we tried to get access to this data, it was a very bureaucratic process, and at the end we didn't get any access to it. So the question also to all the speakers and people in the consortium is if you have similar problems finding in situ data for, let's say, your research topic, or are you really bound to specific in situ data that you only get very locally, or do you have the experience that you get the in situ data you need and the quality you need on the areas you're interested in, or is that something that's limiting you? Because that was my experience so far, but I'd like to know if you share this opinion or if you have similar problems.
Yeah, absolutely. I think the lack of field data, I think it's a problem that we all faced, and initiatives like NASA Harvest or consortiums or like any kind of push for public availability of good quality data, I think will advance the science and will help us develop our models in a better manner. I think Johan wanted to also to say something.
Yes, I wanted just to share my experience with in situ data for the last few years with these bigger projects. Is that in situ data is absolutely the main weakness or the drawback of bigger projects. Well, in situ data is limited, is imperfect, can only from only some point in time, and eventually we use in situ data for validating our models that we develop. That's a requirement. You always need to validate your models to know if they are valid. But what happens when the in situ data is of poor quality, and then the result is that the model is not giving the right retrievals, the right kind of estimations, and these are questions that we are facing. So should we believe, the in situ data or the models that we have been developing? We have been developing the models based on so to say artificial or theoretical data with models and so on, and there it all works perfect. But then once you try to validate it against in situ data, then all the complications start, the hard work and the trouble that eventually sometimes we even decide to give up this kind of in situ data because it blocks us. It cannot makes us further improving our models, that at the end it rather complicates the story than helping us further.
Yeah. Any other thoughts?
And I think since we have now this opportunity in the requirements booth to put ideas and recommendations, this could be one recommendation, because I think all we are suffering from this problem, but it will be very unlikely that individual people can make some changes. I think we need some kind of initiative at a higher level than what individual scientists can do. And we are all suffering from this problem, so maybe it will be a possibility to add these ideas in the forthcoming requirements panel, and then see if ESA or the European Commission or other institutions can do something at this point. Because it's true that at the end we need to validate everything we do, but for instance, in the world of satellite data, there is always the requirement of validating the products. And we are asked to validate the product, but for validating the product, we need some field data, and this is not easy to get in a consistent manner every way. And I think we made a lot of progress in being able to process data now. There were numbers of initiatives, and now everybody is able to process data. But still, for the use of field data, we need some kind of initiative. So maybe it's one of the ideas to promote.
It's also one of the ideas we push in EO4 Agri. This is one of the outcomes I can share, that in situ data on the field level validated is what we are proposing and want to push. Sorry, Oscar, I didn't want to speak over you.
No, it's okay. No, I want to make a comment because it's true. I agree with you of the limitation of in situ data, but also we see there are another doors that are open with the high resolution. It depends what is the granular application that you want, because when we apply with FAO and to support countries, they have to take the decisions now at so granular level like we are showing this moment. And even is the data that is the crop yield data that normally is have a big problem to make the calibration. Now for certain level, if you are thinking to apply for administrative level, Sentinel and other sensors that are high resolution can give the solution to that, like the presentation that we saw before. They are so provide so data that before was impossible. Then we can train it no high resolution, medium resolution, 1 kilometer resolution data with the new high resolution information. I think this is the advantage than before. We can use other indirect measure to collect information about the impact of drought or other hazard in the agriculture. Over.
Yeah, that's right. And well, the other issue is that high spatial resolution data needs also to be calibrated at field level or even within the field. So, and I think that is the most sensitive data for private farmers, or I think there's still some problems on sharing that data. So I think the most important part of our job is to try to convince insurance companies or farmers to help us releasing that data, because at national level, at subnational level, maybe it's easier to get it, especially on closest years. But in the past, also there's a lack of data that maybe can capture extreme events that we were talking about before, how we can improve our models on capturing the impacts of extreme events on the crops. And so the past might be the answer to this question, but it's how we can use that past data that we are missing, right?
May I react quickly on this? You see, when you say crop assurance, we have to see where crop assurance. Something is in Europe about what I think in crop assurance in Africa or Latin America. You are not going to the parcel. You are not going to use this parametric crop assurance at the level. You have to aggregate administrative unit, and you will pay all farmers inside administrative unit. Then the granularity there is not possible. Even government cannot, in a drought in Africa, will need to act parcel by parcel. This is impossible for any government to react at this granular level. Then we need to understand which level is the different applications. Maybe when you are in United States or in Europe, you can pay by parcel, but not in the rest of the world yet.
Yeah, absolutely right. Any further questions? I don't see anyone asking from the audience. Jose, any final
Yeah, well, maybe
thought?
Before closing, because we still have some few minutes, my understanding from the discussion and also from the different presentations is that now there are no major complaints about the availability of data. It seems that we have the satellite data we want. I mean, we're talking about 10 days revisit, seems to be quite okay for most of the applications in this agricultural domain. Spatial resolution, of course, we always want to have higher and higher spatial resolution, but I think with Sentinel-2 at the moment, most users are happy. We have capability to process the data. There are tools available now to process the data. There are algorithms, there are still developments, but there are many possibilities to process the data. And it seems like where we are failing still is on the capability to validate our results. So maybe this is one of the major conclusions out of this discussion, that this is one point where we need to put more. Probably we also need to share more the data processing tools and capabilities, new algorithms and new developments, but this will be always around. But that could be maybe a nice closing point for the discussion which is coming right now. in 2 minutes from now, because we will close this session now and we will move to the other platform where we will have the possibility to exchange ideas. I remember you that there are 2 options in the requirements booth. One is to put questions and answers, so questions to the speakers today, or also can be answered by general people, so it's not necessarily by the speakers, but there will be possibilities for questions and answers in general about the session of today. And there is another possibility in the requirements booth, which is to put your ideas, not necessarily questions, just ideas or recommendations that will be general for the discussion in the scientific domain and in the users' applications. But remember that it's also possible that some of the ideas that you push now in this requirement booth will materialize into some specific actions by ESA and the European Commission in the future programs to make possible some of the things we have been discussing here. So you can see how sometimes you put one idea there and then you see your idea materialize later on. So I will encourage you to participate in this requirements booth discussion and contribute not only with questions and maybe answers also, but also with ideas and recommendations for future activities. And with that, I would like to close. We are exactly at 4 o'clock p.m., so exactly on time. So we have now a short break, and then we will continue with 1 hour discussion through the requirement booth. Thank you very much for all the speakers, and thank you very much for all the people that have participated attending the session through the web, and thank you for all the questions and the discussions we are having.
Thanks also for ESA people, like all the people behind the cameras that are helping to set up this very nice conference. And yeah, thank you so much. See you later.
See you.
Thanks.